Okay, very good morning. Myself Dr.R.Vinoth, working as Associate Professor in the Department of ECE, P.S.R. Engineering College, Sivakasi. Today we will discuss the topic Fourier transform. That is nothing but especially we are going to see the topic discrete Fourier transform. Why we go for discrete Fourier transform? To convert one domain to another domain. And also while solving or while using discrete Fourier transform, let us assume that x of n is the time sequence and consider it as 1, 2, 3 and 4, and let us assume that n is equal to 4. From the definition of DFT, that is nothing but x of k is equal to DFT of x of n, which is equal to, from the definition, summation n is equal to 0 to n minus 1 x of n into w n to the power n into k. Okay. Upon expanding these expressions, x of n k is equal to, upon expanding these expressions, x of k is equal to x of 0 into w n power 0. Why? Because here the limit is n is equal to 0. While multiplying this 0 with k, we get the answer 0 plus x of 1 into w n power. Here we have the term, we are going to substitute only the limit n, and whereas we have the product term k, so that while multiplying n with k, we get k plus, while substituting the third limit, here already we know that n is equal to 4, so that the upper limit will be 3. So x of 1 into w n power n k plus x of 2 into, while substituting the limit n is equal to 2, we get w n to the power 2 into k. Okay. Likewise, while substituting the limit n is equal to 3, we get x of 3 into w n to the power 3 into k. For simple calculations for simple 4-point computation using DFT, we have the expressions like this: x of k is equal to x of 0 w n to the power 0 plus x of 1 w n to the power k plus x of 2 w n to the power 2k plus x of 3 w n to the power 3k. Okay. Here this w n to the power 0, w n to the power k, w n to the power 2k, w n to the power 3k, which means w n to the power n k we can expand as e to the power minus j 2 pi k into n divided by capital N. This we can call it as Tudor factor. Okay. Likewise, and also we can say this as complex multiplication value. Complex multiplication value. Sorry. And while doing this, we need the input is in time domain sequence, which will be multiplied by the complex multiplication value w n to the power 0. Likewise, x of 1 is multiplied with the complex multiplication value w n to the power k, and so on. While doing these operations, we need, let us assume that complex, how many number of complex multiplication required. Here the limit, we have already substituted only the limit of n is equal to 0, but here while finding this, we need to substitute the limit of k also. While substituting k is equal to 0 to 3, the expression will be x of 0 is equal to, while substituting wherever we have k, we are going to substitute 0. Likewise, x of 1, we are going to substitute k is equal to 1. Likewise, x of 2 and x of 3. For simple calculations, simple 4-point computations, we need to have one multiplication, here one multiplication, here one multiplication, and here one multiplication. For finding x of 0, we need 4 complex multiplication values. So, likewise, we have to perform up to x of 3. Therefore, complex multiplication required here is complex multiplication required here is 4 and so on. Likewise, we can consider the complex multiplication here is while getting x of 0 value, we need 4 multiplication values, and for up to x of 3 we have 4 into 4 which is equal to 16, which means for solving 4-point computation using DFT, the complex multiplication required is 16. Now consider complex addition values. Here we have one addition, here one addition, and here one addition. For finding the x of 0 value, we need 3 additions. Likewise, we need to repeat up to x of 3. Therefore, the complex addition required here is complex addition required here is 3 into 4, which means 12. Okay. For a simple 4-point computation using DFT, we need to have 16 number of complex multiplications and 12 number of complex additions. Let us assume that if suppose n is equal to 256, then how about the complex multiplication and the complex addition? It will be unimaginable. 256 into 256, right? Which means we can say that as complex multiplication required to solve 256 values means 256 into 256. It's unimaginable, and also by using this it is somewhat difficult to complete the problem, and also even the computer itself requires much more time to solve this problem. Okay, by getting the output, it needs much more time, so that we need to go for fast Fourier transform. Fast Fourier transform. Fast Fourier transform. From the word itself, we have the meaning fast Fourier transform. This fast Fourier transform is derived by two professors, Cooley and 2K. Two brilliant professors derived the fast Fourier transform to overcome the issues of DFT, which means here Cooley and 2K suggest that if you are going to solve n point DFT of the sequence, simple calculations we are going to perform, which means we can divide the n point into 2. That is nothing but we are going to subdivide n into n by 2 point and here n by 2 point. Simply we are going to divide into 2, which means the whole entire problem is divided into sub problems, then it will get easy and fast results. Likewise, n by 2 we can subdivide into n by 4 point and also n by 4 point. Here also n by 4 point and here also n by 4 point. Okay. Like this we can solve the fast Fourier transforms. Again I repeat, the DFT, in DFT the complex multiplication and complex addition required are more. To overcome these issues, we go for fast Fourier transforms. Fast Fourier transforms was derived by Cooley and 2K, which they are performing is they are subdividing the n point sequences into 2, which means n into n by 2 point and n by 2 point. N by 2 point which will be further subdivided into n by 4 point and n by 4 points, like and so on. Okay. And also one more important point here is while finding or while solving this FFT method, FFT algorithms, the values might be in the range of 4, 8, 12, 16, 32, 64, 128. Why? Because here n is the integer multiplication of 2. Then only we will perform the first Fourier transform. If you are having n is equal to 3, then it is somewhat difficult to get the results. So here n is the integer multiplication of 2, which can be subdivided into 2 and 2. Here 8 is subdivided into 4 and 4 again we can subdivide into 2. Likewise, we can subdivide the values like this. 8 will be subdivided into 4 plus 4. Again 4 will be subdivided into 2 plus 2. Likewise, we have to perform the first Fourier transform operations. Nothing but the integer multiplication of 2. Here n is nothing but the integer multiplication of 2. Okay. So that if you are assuming that 4-point computations, we are going to subdivide this into 2-point and 2-point. Likewise, for 8-point, we need to subdivide this into 4 plus 4, and again we are going to use subdivisions, that is 4 is nothing but we are going to subdivide this into 2 and 2. Likewise, we have to consider 12, 16, 32, 64, 128 and so on. 12 means we need to subdivide this into 6, and 6 again we are going to subdivide into 6 again we can subdivide this into 3, and 3 means this will get the result, but this will have some issues in solving this. We can take n is equal to 3 also, but while taking 1, 3, 5, 7, 11 like these values means it's somewhat difficult to get the results. That's why we have to, as I already said, n is nothing but the integer multiplications of 2. That's why we have to consider 4, 8, 16, 32, 64 and 128. Like this we can assume the computation values. Okay. Here, as I already said, integer multiplication of 2, that's why we can say that as radix to FFT algorithms. Here radix 2 is nothing but we are having two classifications, DIT and DIF. Here DIT denotes that decimation in time. Here DIF denotes that decimation in frequency. In DIT, the sequence might be x of n. Here in DIF, the sequence might be in x of k. That is nothing but in DIT, time sequence is decimated. In DIF, frequency sequence is decimated. That's all. Based on this, we are going to see the classifications of DIT as well as DIF. We are having some, the procedure is same, but we have some differences between these two algorithms, DIT FFT and DIF FFT. In DIT FFT, the input which should be input is in bit reverse order. Here in DIF, input should be in, input is in normal order. Okay. What does it mean, bit reversal order and normal order? We have to take the values, that is x of 0. Suppose we are considering n is equal to 8, then the input might be x of 0, x of 1, x of 2, x of 3, x of 4, x of 5, x of 6 and x of 7. So now let us consider the values 0. We have to write the 0 whole values into binary values, then we get 0, 0, 0. As I already said, n is equal to 8, that's why we have to use 3-bit sequences 0, 0, 0 and 0, 0, 1, 0, 1, 0, 0, 1, 1, sorry, 1, 0, 0, 1, 0, 1, 1, 1, 0 and 1, 1, 1. As like that, we have to write the whole values into binary sequences of using 3-bit sequence. This is nothing but our normal order. Here in DIT FFT, the input should be in bit reverse order. That's why we have to use bit reverse sequence, or we can say that is the mirror image of the normal order. Bit reverse order. We should write the normal order to be converted into mirror image, that is nothing but 0, 0, 0, 1, 0, 0. Here the 1 is transferred to here 1, 0, 0 and 0, 1, 0, 1, 1, 0, 0, 0, 1, 1, 0, 1, 1, 0, 1, 1, 1, 1, 1. Now consider this as the bit reversal order. We should write the bit reversal order in terms of time sequence. So that's why we get the value as x of 0, x of 4, x of 2, x of 6, x of 1, x of 5, x of 3 and x of 7. Like this, we will get the bit reversed time sequence value. That's why if you are having the problem, first you have to write the input sequence, which should be in terms of bit reverse order: x of 0, x of 4, x of 2, x of 6, x of 1, x of 5, x of 3 and x of 7. While solving the problems, we should know how to write the input sequences. Let us see in the next video. Second difference between DIT and DIF is, here the output, we need to consider the output also. Here the output in DIT FFT is output is in output is in normal order. Normal order in the sense we get the output which will be in the form of normal order. But in DIF FFT algorithms, the output is in bit reversed order, which means while solving the problem, after getting the output, we should take the output which should be converted into bit reversed order. That is nothing but first line output should be x of 0, second line output should be the x of 4 values, so that we have to change the sequence and write the output x of n. Okay. Likewise, what about the third important difference is, here as I already saw the input and output sequences, how far it will be written and how it will be normal order and bit reversal order. And third important difference is complex. It depends on the complex addition and complex multiplications. Here in DIT FFT, complex multiplication takes place before the complex add by subtract operations. Okay. As like that in DIF, the complex multiplication takes place after the add by subtract operation, which means before going to do the add subtract operations, we need to multiply the complex values, and here in DIF, after multiplying with the complex multiplication values only, we have to perform the add subtract operations. This is the major difference between DIT and DIF: decimation in time, fast Fourier transform, and decimation in frequency, fast Fourier transform. Okay. We will see the overview and conclusion of this and summary of this today's class. DFT is nothing but discrete Fourier transform. While solving the 4-point computations, the complex multiplication required and complex addition required are more. That's why we have to use, or we have to further go for transforms, another transforms which will help you to complete the problems as early as possible. That's why we go for fast Fourier transforms, which was derived by Cooley and Tukey. They have simply used the rule n point, the whole problem into 2 subdivisions. The whole entire problem is subdivided into 2, and then they will solve the problems. This method will help us to get the results faster, and also we have n is equal to 2. N is nothing but the integer multiplication of 2. That's why we can say that as 4 will be subdivided into 2 again 2, and 8 will be subdivided as 4, and as 4 will be subdivided into 2. Likewise, we can to use the problems, or we have to use the technique to solve the problems. And as already said, n is nothing but the integer multiplication of 2. That's why we have to use radix to FFT algorithms. In radix to FFT algorithms, which will be subdivided into DIT and DIF. DIT is nothing but decimation in time, and DIF is nothing but decimation in frequency. Here x of n, we can denote the x of DIT sequence as x of n, and DIF sequence as x of k, which means that x of n is nothing but, here the time is decimated, and DIF here the frequency is decimated. And also we have seen the difference between DIT and DIF. DIT is nothing but input is in bit reverse order, and input is in DIF input is in normal order. Likewise, the output is in normal order, and in DIF output is in bit reverse order. And also we have seen the complex multiplication and complex addition relations. Complex multiplication takes place before the add subtract operation in DIT, and in DIF complex multiplication takes place after the add subtract operations. Let us see the problem in the next video. Thank you.